Hello students. In today's lecture, we'll study about Bohr's model for hydrogen atom, which is given in the syllabus of class 11 chemistry and rationalized for 2023-24 by NCERT. This is a very important and interesting topic. All the points discussed in this lecture are very important and you please note down. Bohr's model for hydrogen atom. Neil Bohr in the year 1913 was the first to explain quantitatively the general features of structure of hydrogen atom and its spectrum. He used Planck's concept of quantization of energy. Bohr's model for hydrogen atom is based on the following postulates. The electron in the hydrogen atom can move around the nucleus in a circular path or a fixed radius of energy. These paths are called orbits, stationary states, or allowed energy state. These orbits are arranged concentrically around the nucleus as shown in the figure. So it is a black spot is a nucleus. N is equal to 1, 2, 3 are the first orbit is close to the nucleus, second orbit and third orbit, and these orbits are arranged concentrically around the nucleus. The second postulate says the energy of electron in the orbit does not change with time. However, the electron will move from lower stationary state to a higher stationary state, say from orbit 2 to orbit 3, when it absorbs energy. When the electron absorbs energy, or vice versa, the electrons can also move from third orbit to 2 orbit and it emits energy during this fall. So I will read this sentence again. However, the electron will move from a lower stationary state to a higher stationary state when it absorbs energy, or the energy is emitted when electron moves from higher stationary state to lower stationary state. The energy changes does not take place in a continuous manner. Angular momentum. Now first we will try to understand the angular momentum of electron. We know that linear momentum is mass into linear velocity. So the angular momentum is the product of moment of inertia I and angular velocity omega. For an electron of mass m subscript e me moving in a circular path of radius r around the nucleus is given by angular momentum is equal to I cross omega. Since I is equal to MER square and omega is equal to V by R, here V is the linear velocity. Therefore, angular momentum is MER square into V by R, that is equal to ME into VR. The frequency of radiation absorbed or emitted when transition occurs between two stationary states differed by an energy delta E given by Bohr's frequency rule, that is equal to nu. Nu equals delta E by H, where nu is the frequency, delta E is the difference of energy, and H is the Planck's constant. So delta E can be represented as E2 minus E1 divided by H. Here E1 and E2 are energies of lower and higher allowed energy states respectively. The angular momentum of an electron is quantized. In a given stationary state, it can be expressed as MEVR equals N into H by 2 pi. Here N is an integer and N is equal to 1, 2, 3, etc. a whole number. And V, capital V, is the velocity. So an electron can move only in those orbits for which its angular momentum is an integral multiple of h by 2 pi. So it is an integral multiple of h by 2 pi as given in expression 11. That means angular momentum is quantized. Radiation is emitted or absorbed only when transition of electron takes place from one quantized value to another quantized value of angular momentum. So these are all quantized numbers. To repeat, me is the mass of electron, v is the velocity, and r is the radius of orbit in which electron moves. Bohr's theory for hydrogen atoms. The details regarding the derivation of energies of stationary states used by Niels Bohr are quite complicated, and these will be dealt in higher classes. In this session and in this slide, I will give you just an insight of it. According to the Bohr, the stationary states of electrons are numbered n equals 1, 2, 3, etc. etc. These integral numbers are known as principal quantum numbers. Please note principal quantum numbers. Next point. The radii of stationary states are expressed as Rn is equal to n square into A naught. Let it be equation 12. Here the value of A naught equals 52.9 picometers. Note 52.9 picometer. Thus, the radius of first stationary state is called Bohr's orbit. So, the radius of first stationary state is called the Bohr's orbit, and its radius is 52.9 picometers. Normally, the electron in the hydrogen atom is found in this orbit, that is n equal to 1. As we increase the value of 1 n, that is as n increases, the value of r will also increase. In other words, the electron will be present away from the nucleus. So, as n increases, the electrons will be farther away from nucleus. Next point. The most important property associated with electron is energy of its stationary state. It is given by the relation En is equal to E subscript n is equal to minus R subscript h into 1 by n square. And here the value of n is 1, 2, 3, that is an integer and whole number. Let it be equation 30. Hence, E is the energy of the stationary state. RH is the Rydberg constant. RH is called the Rydberg constant, and its value is, numerical value is 2.18 into 10 to the power of minus 18 joules. The energy of the lowest state is called the ground state. That is, if we put the value of n equals 1 in equation 13, we get the energy of the lowest state, that is called ground state. For example, E1, n is equal to 1 is E1 equals 2.18 into 10 to the power of minus 18. the energy of the next state, that is, if we put n equals to 2, then E2 will be equal to minus 0.545 into 10 to the power of minus 18 joules. So energy is in joules. Please see the figure shown on your screen. This figure shows the energy of different stationary states or energy levels of hydrogen atom. This diagram or the figure is for hydrogen atom, and this representation is called the energy level diagram. Here you please see this is the ground state. N is equal to 1 is a ground state, and maximum value of N is N infinity, where the energy level is 0. So maximum energy is at the bottom, and the energy is 0 when N is equal to infinity. When electron is free from the influence of nucleus, the energy is taken as 0. So here at the 0 level, the electron is free from the influence of nucleus. The electron in this situation is associated with the stationary state of principal quantum number, that is equal to n equals infinity, and is called the ionized hydrogen atom. So in this energy state, it is ionized hydrogen atom. When electron is attracted by the nucleus and is present in the orbit n, the energy is emitted and its energy is lowered. That is the hydrogen for that is the reason for presence of negative sign in the 13. So I will read this once again. When the electron is attracted by the nucleus and is present in orbit n, the energy is emitted and its energy is lowered. That is the reason for the presence of negative sign in equation number 13. And it depicts the stability relative to the reference state of zero energy, that is n equals infinity. We will continue with Bohr's theory of ions containing one electron. Before that, we will go through the meaning of negative electronic energy En as expressed in equation number 13. The energy of electron in a hydrogen atom has a negative sign for all possible orbits, as we have seen in equation number 13. This negative sign means that energy of electron in the atom is lower than the energy of free electron at state. So electron in the energy state in the atom is lower than the energy of free electron at rest. A free electron at rest is an electron that is infinitely far away from nucleus and is assigned the energy value of 0. Mathematically, this corresponds to setting n equal to infinity in equation 13, so that E infinity is 0. As the electron gets closer to the nucleus, n decreases, that is, the number of the orbit decreases. E infinity becomes larger in absolute value and more negative. The most negative energy value is given by n equals 1, which correspond to the most stable orbit. This is called the ground state. So next we will take up point number D. Bohr's theory can also be applied to ions containing only one electron, similar to that present in hydrogen atom. For example, helium, lithium, etc. and so on. The energies of stationary states associated with these kinds of ions, also known as hydrogen-like ions, are given by the expression En is equal to 2.18 into 10 to the power of minus 18 into Z square by N square joules. Let it be equation 14. And its radius is given by the relationship Rn is equal to 52.9 N square divided by Z picometers. So let it be equation 15. Here Z is the atomic number and has values 2, 3, etc. for helium and lithium atoms respectively. 2, 3, 2 for helium and 3 for lithium. The value of atomic number Z. The value of energy becomes more negative and that of radius becomes smaller with increase in value of Z. This means that electron will be tightly bound to the nucleus. And last and final postulate point is quantitatively the magnitude of velocity of electron increases with the increase of positive charge on the nucleus and decreases with the increase of principal quantum numbers. Explanation of line spectrum of hydrogen. The line spectrum of hydrogen can be explained quantitatively using Bohrs model. According to assumption number 2, the energy or the radiation is absorbed if the electron moves from smaller orbit, that is, say for example n is equal to 1 to the orbit number 2 of the principal quantum number. In the other case, the radiation or the energy is emitted. Please underline emitted if the electron moves from higher orbit. So that is, if it moves from higher orbit number 2 to lower orbit number 1. The energy gap between the two orbits is given by the expression delta E is equal to EF minus E1. Let it be equation 16. Here EF is the energy of the final state and EI is the energy of the initial state, and the difference between the two is given by delta E. Now combining equation 13, which we studied in the earlier slides, that is equation 13 is En is equal to minus RH into 1 over n square, where n is an integer, n is equal to 1, 2, 3, etc. etc. RH is the Rydberg constant and En is the energy level of that particular orbit. So substituting the value of En from equation 13 for EF and EI and simplifying, we get delta E is equal to EF minus EI equals 2.18 into 10 to the power of minus 18 joules into 1 over Ni square minus 1 over Nf square. Let it be equation 17. The frequency nu of photon is evaluated by using the expression nu, that is frequency nu is equal to delta E by h. Here h is the Planck's constant and frequency is nu, and delta E is the energy gap, that is equal to RH divided by h into 1 over Ni square minus Nf square hertz. So this here in equation 18 we have substituted the value of delta E from equation 17. So substituting the numerical values of Rydberg constant RH and Planck's constant, we get 2.18 into 10 to the power of minus 18 joules divided by 6.626 into 10 to the power of minus 34 joule seconds into 1 over Ni square minus 1 over Nf square. Simplifying, we get this equation for frequency as 3.29 into 10 to the power of 15 into 1 over Ni square minus 1 over Nf square hertz. Let it be equation 19. See, this hertz it has come because it is 1 over s. J and j gets cancelled. 1 over s is hertz. Let it be equation 19. Similarly, we can calculate the wave number nu bar equals V by C, where nu is the frequency and C is the velocity of light. That is equal to nu value you substitute from equation 19, that is RH divided by h into RH by h into 1 over Ni square minus 1 over Nf square. So nu is from equation 18 and the value of C as it is we can put it. Let it be equation 20. So substituting the value of C, that is velocity of light, as 3 into 10 to the power of 8 meters per second, we get a new formula, that is 1.09677 into 10 to the power of 7 into 1 over Ni square minus 1 over Nf square per meter. Let it be equation 29. Now let us analyze and interpret the meaning of equation 17. So in equation 17, if Nf is greater than Ni, the term in the bracket is positive and the energy is absorbed. So when the term is positive, the energy is absorbed. Whereas if Ni is greater than Nf, E is negative. So the energy is released. The expression 17 is similar to that used by Rydberg. So who calculated the wave number nu bar equal to 109,677 into 1 over Ni square minus 1 over N2 square per centimeter. This is from equation number 9. You please go back and see the calculation. This was derived empirically using the experimental data available at that time. Further, each spectrum line, whether in the absorption or emission spectrum, can be associated to the particular transition in hydrogen atom. So we can give the numbers for spectral line and we can see whether it is absorption or an emission spectrum. In case of large number of hydrogen atoms, different possible transitions can be observed and thus leading to the large number of spectral lines. The brightness or intensity of the spectral lines depends upon the number of photons of the same wavelength or frequency absorbed or emitted. Please remember, the brightness of the spectral lines depends on the number of photons of the same wavelength or frequency absorbed or emitted. Now we'll take up some worked examples. Example number 10. What are the frequency I wavelength of a photon emitted during a transition from n is equal to 5 state to n is equal to 2 state in the hydrogen atom? Answer. Using the formula delta E is equal to 2.18 into 10 to the power of minus 18 joules into, open the big bracket, 1 over Ni square minus 1 over Nf square joules. This is given in the equation number 17. So delta E is equal to, we can substitute the value of Ni, that is transition from Ni. The initial state is 5 here and the final state is, that is Nf is equal to 2. Substituting Ni is equal to 5 and Nf is equal to 2 and calculating the delta E, we get the value as minus 4.58 into 10 to the power of minus 90 joules. Please do the calculation yourself. It is an emission energy because there is a negative sign. The frequency of the photon taking energy in terms of magnitude is given by frequency is equal to nu is equal to delta E by h, where nu is the frequency, delta E is the energy and h is the Planck's constant. Substitute the value of delta E calculated in the previous step. So we get, simplifying, we get the answer as 6.91 into 10 to the power of 14 hertz. And with this value, we can calculate the wavelength. So the wavelength is given by the formula lambda is equal to c by nu, where lambda is the wavelength equals c by nu. That is equal to c, the value of c, that is velocity of light in vacuum, is equal to 3.0 into 10 to the power of 8 meters per second. You have to remember these constant values of h, values of c, etc. for solving this problem. That is equal to 3.0 into 10 to the power of 8 meters per second divided by, we have calculated the value of frequency in the previous step as 6.91 into 10 to the power of 14 hertz. Simplifying, we get the answer as 434 nanometers. This is the answer. Next question. Calculate the energy associated with the first orbit of helium plus. What is the radius of this orbit? Answer. En is equal to minus 2.18 into 10 to the power of minus 18 joules into Z square by N square per atom. This is the energy per atom. Please note and write down this. For helium plus, N is equal to 1 and Z is equal to 2. Z is the atomic number, N is the number of orbit, because they have asked in first orbit. Therefore, En is equal to, substituting in the above formula, En is equal to minus 2.18 into 10 to the power of minus 18 joules into 2 square divided by 1 square joules. That is equal to minus 8.72 into 10 to the power of minus 18. Now we have to further calculate the radius of orbit, as given by the equation Rn is equal to 0.0529 nanometers divided by Z, that is equal to, substituting the values, Rn is equal to 0.0529 nanometers into n square is 1 square divided by 2, because Z is equal to 2. Simplifying, we get the answer as 0.02645 nanometers. This is the answer, and this is the radius. Bohr's model of hydrogen atom was no doubt an improvement over the Rutherford's nuclear model, as it could account for the stability and line spectra of hydrogen atom and hydrogen-like atoms like helium, lithium, etc. However, Bohr's model was too simple to account for the following points. That is, the following are the limitations of Bohr's model. Bohr's model fails to account for the finer details of the hydrogen atom spectrum observed by using sophisticated spectroscopic techniques. This model is also unable to explain the spectrum of atoms other than hydrogen. For example, it cannot explain helium atom, which possesses only 2 electrons. Further, Bohr's theory was also unable to explain the splitting of spectral lines in presence of magnetic field and electric field. So again, shortcomings were, it was not able to account for the hydrogen atom observed by sophisticated spectroscopic techniques. So that model is different from this model. This model is also unable to explain the spectrum of atoms other than hydrogen. That is, it could explain for only hydrogen. It could not explain for helium atom or other atoms, which helium atom is which possesses 2 electrons. Similarly, the Bohr's theory was not able to explain the splitting of spectral lines in presence of magnetic field and electric field. That is, Zeeman effect and Stark effect showed the splitting of spectral lines of hydrogen atom, and Bohr's model could not explain that. Next is, it could not explain the ability of atoms to form molecules by chemical bonding. Now we'll continue with answering some multiple choice questions. As you know, the multiple choice questions, 4 options will be given and you have to choose the correct answer. So let us start. First question. The electron in Bohr's model of hydrogen atom is pictured as revolving around the nucleus in order to: option A, emit photons; B, keep from being pulled into the nucleus; option C, keep from being repelled into by the nucleus; D, possesses energy. You have to choose the correct answer. Please analyze, remember and recall that revolving electrons possess energy. So this option is given as option D. Please mark it. Next question. What is the color corresponding to the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from n is equal to 4 to n is equal to 2? 4 options are given. Option A, blue; option B, red; option C, yellow; and option D, green. Please read the question. And in the question, we are asked what is the color corresponding to the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from n is equal to 4 to 2. Now we have to do some calculations. The calculations are shown in the inside box. Recall the formula 1 by lambda is equal to r into 1 over n square minus 1 over n1 square minus n2 square. So that is equal to 109677 into 1 over 2 square minus 4 square. Here in the question it is given we have to find when the electron is going transition, it is falling from n is equal to 4, that is ni is equal to 4 and nf is equal to 2, and this we have used this formula and calculated the value as 20564.4 per centimeter. Therefore the lambda, because we have calculated 1 over lambda and we have to calculate lambda, therefore lambda is equal to 1 over 20564.4 per centimeter. So the value comes to 486 into 10 to the power of minus 9. So this color corresponds to the wavelength whose wavelength is blue. The color corresponding to this wavelength is blue. Hence, please mark the option A, which is correct. Next question. Which of the following series of lines are the only lines in hydrogen spectrum which appear in visible light? As you know, there are so many series of lines which are falling under infrared region, ultraviolet rays and visible light. So you have to identify. You are given 4 options. First, Lehman series, option B, Balmer series, option C, Bastian series and option D, bracket series. So you have to remember. You have to remember that in Balmer series, the lines appear in visible region. This option is given as option B. Please mark it. Next question. An electron in excited hydrogen atom falls from 5th energy level to 2nd energy level. In which of the following regions the spectral lines will be observed and is part of which series of spectrum? So please read the questions again. We have to identify the region and the spectral line, region of spectral line and part of the series. So 4 options are given. These 4 options are appearing on your screen. Option A, visible Bohr's line. Option B, ultraviolet Lyman. Option C, infrared and Passion. And option D is infrared bracket. Remembering, in Balmer series, n1 is equal to 2 and n2 is equal can be 3, 4, 5, etc. etc. These lines appear in visible range, visible region. So this is option A, given in option A. Please mark it. Next question. Next question is on your screen. The frequency of radiation absorbed or emitted when radiations occur between two stationary states with energies E1 and E2. E1 is a lower energy level and E2 is the higher energy level is given by, you have to identify the correct formula. 4 options are given. The 4 options are appearing on your screen as option A, option B, option C and option D. Please read all the options and mark the correct answer. And you have to remember that when the energy, then when the energy is emitted, radiations occur when energy is emitted from higher level to lower level. So correct formula is option D, that is nu is equal to E2 minus E1 divided by H. You have to remember and quickly mark option D as the correct answer. Next question. According to Bohr's theory, the angular momentum of electron is in the fifth orbit is. You have to calculate the angular momentum. So, four options are given and these options are appearing on your screen as option A, option B, option C and option D. Please read it and do the calculation and recall. So we should remember that angular momentum is m into v into r, where m is the mass of an electron, v is the velocity and r is the radius. MVR, angular momentum, is given by the formula nh divided by 2 pi. N is the orbit number and h is the Planck's constant. So put n is equal to 5, which is given in the question. So 5h by 2 pi. 5 by 2 is 2.5. So here angular momentum is coming as, the answer is coming as 2.5 h by pi. And this option is appearing as choice D. Please mark it. So D is the correct answer. Next question. The radius of stationary state, which is also called Bohr's radius, is given by the expressions. And you have to calculate and identify the correct formula. So four options are given: 52.9 picometers, 5.29 picometers, 529 picometers, and option D 0.529 picometers. You have to do some calculations. Rn is equal to, we should remember the formula. Rn is equal to 52.9 into n square divided by z. And the value of 52.9 divided by z is A0. So this value is 52.9 is appearing as option A. Please mark it. Next question. What is the trend of energy of Bohr's orbits? Option A, energy of the orbit increases as we move away from the nucleus. Option B, energy of the orbit decreases as we move away from the nucleus. Option C, energy of the orbit remains same as we move away from the nucleus. And option D is energy of the Bohr's orbit cannot be calculated. Please remember and recall the correct answer and mark the correct answer. The energy of the orbit increases as we move away from the nucleus or as the value of n increases. Hence, we have to mark the option A as the correct answer. With this, we come to the conclusion of lecture number 3. And now next lecture we will discuss about towards quantum mechanical model of atom. Till then, goodbye.